Welcome back, and let us resume our discussion on the dual loop common mode feedback and contrast it with the single loop common mode feedback that we were discussing. So we have discussed the basic advantage over here that in the two stage common mode feedbacks we are having the advantage of setting the bandwidth of the common mode loop and the differential loop separately and optimize them separately, whereas for the earlier case that we had discussed for the single loop common mode feedback, we had noticed that the overall bandwidth of the common mode loop as well as differential loop would be dictated by the single CC that was used for compensating both the loops. So, there of course, both the loops are constrained to the same bandwidth, and that may not be the optimal case, and that is the major advantage that you can say for a two loop common mode feedback for the two stage op amp. For the single stage, a couple of other issues that we need to also address, and couple of questions that were asked regarding the single loop compensation. I would like to briefly address that before we proceed towards next topic and continue our discussion on cascade amplifier that we started last day. So, here if I revert back to our previous discussion on single loop, we argued that to keep the amplifier, the overall loop gain for the common mode feedback within bound or within reasonable value, we would like to keep the error amplifier diode connected. So, we would replace this current mirror load by the diode connected load, so that the gain of the error amplifier becomes unity, and then traversing the loop you have overall GMRO square gain. If you keep this current mirror load, then of course for the two loops we have GMRO whole cube, and then the compensation and stability can become more difficult, more challenging for the overall common mode loop. So, let us revisit that case and try to see let us try to address couple of other queries related to single loop feedback. Particularly one of them was interesting, and it has got to do with joint compensation of common mode and differential. So, here once again we are assuming that the output common mode is taken from the final output stage. So, if this is your Vi plus and Vi minus, I have the Vo plus and Vo minus, and my error amplifier is going to take the Vi plus Vi minus VCM ref, and this is going to be close to VDD by 2, because this is the output common mode. I would like the output common mode to be VDD by 2, and then you have and we had reversed the polarity. If you remember, just to satisfy negative feedback, I have to take the output over here, because if the common mode over here goes up, that means the signal over here will be going down, and that will be bringing the PMOS gate voltage down, that will make this up, and as a result this will again be brought down. So, I would have the reverse polarity for the error amplifier. So, this is what we discussed, and we also suggested that let us get rid of the current mirror load and have a diode connected load, disconnect this node. Of course, you have to, for the diode connected load, you have to disconnect this, otherwise you are shorting both the outputs. So, you have to disconnect this central connection and make both of them diode connected, so that the gain of this stage is given by GM1 upon GM2, and as a result you are having overall gain of the common mode feedback loop given by GMRO of the two stages. This is going to give you unity. And there also we discussed that in this particular case the best place to put the compensation capacitor would be this only, because this is a high impedance node, this is a high impedance node, and the gain from this point to this point is also large GMRO. As a result, you can get a sufficiently large Miller multiplied capacitor over here, whereas this node we have converted into a low impedance node, and as a result if you put a capacitor over here, it is not going to give you any significant advantage, because the impedance at this node is low, and therefore the pole over here will be at relatively higher frequency. It will be difficult or infeasible to make this the dominant pole if we are choosing to put a direct connected load for both the transistors over here. So, this was the natural choice we arrived at, and we concluded that this CC is also going to compensate the differential loop. So, both the sides we are putting the same CC is also going to compensate the differential loop, and both the bandwidth for the differential loop as well as common mode loop are going to be governed by the CC only, and therefore, we do not have the freedom to optimize both of them separately. That is what we discussed last time, and therefore, we explored the alternative where we can have two isolate loops, two different loops. And then we just now discuss the transistor level implementation of both the loops and the stability considerations, looking at the conflict between the two loops and making sure that the stability analysis of one of them is not influenced by the other. So, this is an important conclusion that we just arrived at. Now, here another important question was that can we go for a compensation cap between the output of the error amplifier and the second stage, and in that case can we go for a current mirror load. So, if I stick to current mirror load, that means this stage is going to have a large gain of GMRO, and then put a cap between these 2 points, for the compensation of the common mode loop. This is what is going to be the pros and cons, whether it is a good scheme, whether it is going to give us appropriate compensation for the overall loop response for the common mode. So, once again, first of all, we need to make sure that it is not disrupting my differential operation, it is not disturbing my bias point, not the bias point, but actually the frequency response for the differential operation. So, once again, if I assume that for the differential operation, this overall common mode signal is not so strong and the common mode level is not disturbed. So, for the differential signal, this is always AC ground. For the differential half operation, this point is not going to have any signal. As a result, once again, for the output node, CC is going to appear as an additional load capacitance. So, in fact, it is able to mitigate any interaction between the CC and the load or the effective capacitance coming at the first node. Now, the only way the common mode response and the differential response is going to interact is the effective CC coming at the output node. For the differential response, we will have to represent the CC at the output node, between output node and AC ground, because for the differential response, this is AC ground. So, that is well and good, that does not really interfere with our differential response. For the common mode response, the advantage we are getting over here is that from this point to this point, gain is GMRO square, and as a result, the multiplication that you get for the CC will be large, and hence the effective capacitance over here can be pretty large. So, the effective capacitance that you get over here, C Miller if I call it. So, C Miller will be of the order of GMRO square times the CC, which can be significantly larger as compared to GMRO times CC, 100 times larger, and it will give us advantage only if this is a current mirror load. If this is a diode connected load, then once again pole at this point, pole of error amplifier, if I call it PE at this particular point, that will still be given by 1 upon GM RO square times CC times the impedance over here. For the diode connected case would have been just 1 upon GM, that would just lead to GM RO square times CC, which is going to be similar to what we get over here. So, however, if I have this current source current mirror load, in that case the impedance over here is large, it is close to RO by 2. So, the order of the pole GM RO square times CC times RO, this can be pretty small, it can push the pole towards low frequency. So, it can help us in achieving better compensation expectedly. So, at the higher level, if I look at it, it can push the pole at P towards lower frequency. So, that because of larger Miller multiplication achieved by CC. But the other issue is for the differential operation, once again we are going to anyway have the CC, the green ones which are coming into picture. For if I am compensating the loop with CC between the output of the first stage and the second stage, the effect is that the dominant pole over here gets pushed down towards lower frequency, at the same time the second pole over here gets pushed towards higher frequency. So that helps in pole splitting and achieving a overall good phase margin. But in this case, if I look at the overall common mode loop, for the common mode loop, this Cc is still going to come into picture between the output of the first stage and the output of the second stage, which is again going to have a Miller multiplication, and as a result this is also going to be another pole over here, which is going to be I can call it P1, which is going to be given by Gm Ro times Cc. I am just looking at the order, so just ignore the factors of half and all that you get because of Ro by 2, etc. I am just looking at the order. So Gm Ro times, I can call this, just assume that these two Cc are also close. So Gm Ro times Cc times Ro, you are going to get another pole P1 over here. And if I look at the ratios of the Pe and P1 in the common mode loop, we are going to get a ratio of Gm Ro. So if I look at the ratio of the higher pole P1 upon Pe under this scenario, it is going to give you Gm Ro, which is not sufficient for getting a 45-degree phase margin, right. In order to get a 45-degree phase margin, as we have seen, the ratio should be equal to Gm Ro square, the overall open loop gain of the amplifier Gm Ro square times the first pole should be equal to the second pole, or the dominant pole times the open loop gain of the amplifier should be the second pole. So that is going to give me 45-degree phase margin. And how is it ensured? If I use Cc over here, in that case we have seen that the impedance at the second node, at the output node, becomes approximately 1 upon Gm of that stage, and as a result the P2 that you get for the two stage compensation, the P2 that you get is close to Gm upon the overall Cl that you have at this node, and the P1 that you get is Ro times the compensation capacitor, Miller multiplied compensation capacitor, so Cc times Gm Ro. So this is the order of the two poles that I get when I am using Miller compensation between the output of the between the input of the second stage and output of the second stage. And here I can see that the ratio of P2 upon P1 is going to be given by Gm Ro square times Cc upon Cl. If I assume that these two are close together, I can say that the order of magnitude of P2 upon P1 is Gm Ro square, which is good for or sufficient for giving me a 45-degree phase margin. Whereas if I use a Cc over here and use a current mirror load over here, what I am seeing is that the ratio of the two poles is Gm Ro, which is going to be very difficult to achieve 45-degree phase margin over here. Only way you can do that is you use a Cc, the blue Cc should be much larger. If you use that much larger than the Cc used for the differential operation, then possibly you can achieve that. And in that case, you can also possibly go for Ro over here, which is much larger than the Ro of the first stage of the differential amplifier. In that way, possibly you can still try to achieve the C Miller over here, which is much larger than the Miller multiplication of Cc for the differential operation. So there are two constraints that will come into picture, that you need to use a large, let me call this Cc1 just to distinguish, or Cc star. You will have to use large Cc star so that this node becomes dominant and the pole contributed by the second one is still much lower. So I would like to ensure this ratio P1 upon Pe to be Gm Ro square. So that means that the ratio of Cc and Cc star and C must be pretty large, or in other words, Cc star times the Ro of this stage divided by the Miller multiplied capacitance of Cc times Ro of this stage should be pretty large. So it has, of course, trade-offs with area. So you will have to put a lot of area to obtain an overall 45-degree phase margin for this scheme. Advantage will be that yes, you can compensate the two loops in a very different fashion. You can have the common mode loop with much lower bandwidth as compared to the differential loop. So, you are able to isolate these two pretty well, but at the same time you are having to pay a heavy price in terms of much larger CC star required, or you may have to go for a larger RO over here. And then once again, if you look at the loop gain, in order to get advantage of this mirror multiplication, the loop gain over here should be GM RO cube, because this has to be current mirror load, then only you will get a large impedance over here and any advantage of the CC star. So, in that case the loop gain becomes GM RO cube, and that can further interfere with the stability. It can make the compensation a little more challenging. So, this choice it may have negative impact on the overall design for the two stage op amp. So, this is another issue that we should keep in mind. You can try it out, you can in the simulation you can try it out, that if you are trying to apply this scheme and putting a CC star between the output of the error amplifier and the output of the op amp, whether you are able to isolate the two loops properly, and you are able to have the compensation for the common mode feedback achieving enough phase margin. You will notice that you will either require to make the RO of this stage pretty large, or you will like to make the CC star pretty large as compared to CC. So, area trade off and also stability becomes more challenging. So, while you are trying to solve or isolate the common mode compensation from the differential compensation with the help of this, hoping to have a better compensation for the common mode, we can see that the in the overall picture you can end up messing up the stability of the common mode. So, this is another option that can come to mind if you look at where to put the capacitor for the differential and the common mode. So, the common mode we can say that okay, hopefully we can take advantage of this one, but we are seeing some issues. This point is clear. So, in one of the assignments we can ask you to use CC star for compensating the common mode feedback loop, and see what is the value of CC star required to achieve common mode stability while having a CC for differential stability as well. So, in presence of CC, how do you use CC star, how do you find out the right value of CC star for getting the stability for the common mode loop. So, that also has to be taken care of. So, if you have any question regarding this, how to what are the concepts involved and why we are probably not going with this connection CC star, it should be clear enough before we proceed towards our next topic. So, overall stability analysis, having these three loops together, it is a good exercise. So, in general, if you are going for more complicated circuits, maybe filters, there also similar concepts apply. You may have multiple loops and you have to take care of the stability of those loops. Likewise, when we go for switch capacitor circuits or more complicated feedback systems, signal delta modulators for ADCs and so on, there you have similar cases. We have multiple loops where we need to take care of stability of each of those loops. So, here we are dealing with the front end amplifier only and trying to see the stability considerations in order to make the DC point stable enough, and at the same time make the differential response stable. So, and whatever simulation exercises have been recommended so far, they are very much aligned with the discussions we had for the single loop common mode feedback, as well as now we have done detailed discussion on the dual loop common mode feedback. So, there is a good combination. The DC biasing point also, you should be aware of the kind of amplifiers to use whenever you are requiring feedback, kind of topology to use, whether you use a PMOS input device, NMOS input device, what kind of DC biasing to get for references, etc. And then when you are looking at multiple loops, how to look at their interaction, whether the compensation in one loop is interfering with the compensation of the other loop, whether the compensation of common mode feedback is interfering with the differential compensation. So, those things are important to be understood, so that you can appreciate what is going on in the simulation, and you can in fact check those effects. Like if you are for example, the interference of the common mode feedback, you can check whether we are looking at the stability of the differential loop, the first common mode loop. If you are deactivating the second common loop, what happens? So, there are nice examples that will help you understand the overall interactions between these loops. Likewise, this is also a nice example where rather than putting this CC for the compensation, I am allowing this to be high impedance, I am allowing this to be large gain GMRO by putting a current mirror load, and then I am putting a CC star, and then trying to see whether this scheme at all helps me in getting compensation. What are the pros and cons. So all this analysis we try to do will give you a better idea of the design choices that we are making. So even if that's not a good choice in some condition, in some other conditions it may become a good choice where you are possibly area constraint is smaller and you want to have common mode having much lesser current, so that the gain of the stage is large and you are having a large RO anyway. So in those cases you may end up using it. So if you are simulating it and trying to see what is the disadvantage, you should be at least aware of this trade-off. So in the simulation exercises, you should apart from following the step that has been suggested, you have to go one step further and try to think about the problem at hand a little bit more deeply, whether it is just DC biasing, whether it is frequency response, whether it is noise analysis. So another exercise on noise analysis also has been suggested, where you have to size the transistor appropriately so that the 1/f noise corner is pushed towards lower frequency, and then you have to make sure that the bandwidth of the differential amplifier for the differential operation along with the CC compensation is sufficiently higher than the 1/f corner frequency. So that is another interesting example you can look at. So just designing this front-end amplifier is having so many trade-offs. So so far we have not given you a transistor level design example where you can at least estimate the values of the CC and the transistor sizes W by L, etc. Given higher level specs. So here I have just shown you so far the steps for analysis, that okay, for noise analysis this is the step, this is the sizing direction through which you can reduce the noise, this is the ways you can compensate the differential loop and common mode loop, but there can we need to take another example where given these specs at higher level that we have arrived for our front end amplifier, how to arrive at these values of CC, CC star, or the sizes of these transistors. So calculations can give you a starting point, and in general from that starting point you can do the simulations and you can tune the transistor dimensions or the component values in the right direction to approach the right specs. So in general for calculations we will be using second order model, which is not very accurate, of course. It just gives you a starting point that if you have estimates of the device parameters, or you have the values of the device parameters given from the technology, like the K and Kp of the MOSFET, the noise parameters of the MOSFET, the lambda value of the MOSFET, if you have these parameters given, or even if you can estimate these parameters, like in the second order model we use just lambda VDS, and that lambda is not explicitly mentioned in the higher order models. It depends on many other parameters. So in order to extract the parameters that you use for second order calculation, you can do a DC sweep on your MOSFET and extract what is the effective lambda. So ultimately you are using long channel length, right? So MOSFET in the analog design you will be using long channel length 1 micrometer. It's not really that if you are using 180 nanometer channel length, the devices will be here minimum channel length. We are using pretty large channel lengths. For example, for noise we consider this to be having much larger channel length, so that you can have a input referred noise small, or the 1/f noise corners can be pushed towards lower frequency. So that enforced us using long channel lengths for this one, maybe even 10 micrometer. That is pretty common. Even for 180 nanometer devices, you may be using a channel length for these guys which are probably 10 micrometer, 20 micrometer. That is not uncommon. Likewise, for the input devices, you are probably using at least few micrometers so that the gain is sufficient. So the devices that you are using are relatively long channel, although you are going for scale technology. Scale technology may give you advantages in terms of noise, in terms of the FT of the devices, but in order to maintain overall integrity of the analog signal, in order to get a better RO, or in order to get a good input referred noise, good stability and compensation, we are seeing that ultimately we are forced to use longer channel lengths for these devices, and therefore the second order model is good enough for most of the analysis or most of the health calculation you will be doing to arrive at the required sizes. And for that you don't have for this, for example, if you are using a PTM 180 nanometer model in your LT spice simulation, or even some TSMC or UMC model in your cadence simulation, they are using much more higher level models. but from the DC analysis for this device dimension, you can calculate, you can estimate what is your GM, what is your RO, what is your KN, KP, what is your lambda, and based on that you can do some hand calculation and estimate what is the W by L etc. required for meeting certain specs. There are some other specs also that we have discussed in earlier classes, like the input swing, input common mode range, output common mode range, combined together with other specs that we have discussed: noise, bandwidth, stability, there are some others like slew rate etc. that will be coming into picture, common mode ejection ratio. All these combined together, so many parameters combined together will be leading us to some initial values of W by L and the CC, the compensation capacitor, other components etc. required. So, we will take one example where whatever analysis we have done for these different properties, noise, bandwidth, stability, input swing, common mode range, that will be combined together, giving us some starting point for the device dimension and the component values with which we can start the design, and then based on the simulation results we can fine tune the design in the right direction to get closer and closer to the spec, or get better and better in terms of optimization of various matrices like power consumption, noise and bandwidth, resolution etc.
Yes sir, we are not fixing the output common mode level of the first stage. That is VO1 plus and VO1 minus. How are we fixing the output common mode level of the first stage?
No, so this is the ultimately the output common mode is provided over here. The input of this error amplifier in this case is VO plus VO minus.
No, for the first stage.
That is assume that it is fixed with the help of the voltage over here. So, the error amplifier output will provide a certain voltage over here, which will lead to a required voltage over here to get a desired voltage at the output. That is what happens in the single loop. So, we are not directly enforcing certain voltage over here. In the case of dual loop, we are enforcing certain voltage over here, which is equal to the VGP of MOSFET, and we discuss what is the logic behind that. But in this case, we are not controlling this directly, allowing the single loop to establish a desired voltage over here, which is required to establish our desired common mode over here. So, if the common mode over here is going up, I would like this voltage to be going up as well, so that it goes down. So, that is it, that would require that this voltage should be going down. So, that would require that error amplifier should be going down, so that this is going down, and as a result this is going up, as a result this goes down. So, this is controlled by the common mode feedback, and there one of the other issues is that you do not have a very fine control over this. This can end up being too low also or too high also, and therefore, the transistor over here can end up in triode more easily. Whereas, when you are defining this at a desired point, say equal to VGP, then it is much more ensured, or you are having appropriate DC point over here. So, that is another advantage of using dual loops. You have a well defined voltage over here, which is you are setting equal to a desired value. But when you are looking at only the output and you are allowing the feedback to set the value over here, this is only dependent upon the common mode feedback. It can be it can go low or high depending upon the loop response, and then the first stage can end up being in trouble. We will resume our discussion on cascode.